Hi everyone, this is video 2 for chapter 5. I intended to start section 5.2 right now, but I just realized I forgot to mention one thing from 5.1, which is pretty important. So let's just first cover that before moving on to 5.2. Okay, what we need to look at is the cumulative distribution function. So you remember what the cumulative distribution function of a random variable is? Well, what do you have? So the cumulative distribution function evaluated at any real value a is the probability that the random variable is less than or equal to a, right? Or we could also write this as the probability that x belongs to the set minus infinity to a. Okay? For a continuous random variable, it really doesn't matter if that parentheses, you write that as an open bracket or a closed bracket, it doesn't matter because the probability x equals that value is 0. Okay, and also now for a continuous random variable, what do you have this equaling? You know this equals the integral from minus infinity to a of the probability density function of the random variable. So what do you have? F of a equals my integral minus infinity to a of f of x dx, where little f is the probability density function. Okay, well, stare at that for a moment and ask yourself, what does that remind you of? It should remind you about something you've seen in Calc 1. Do you remember? Well, this should remind you of the fundamental theorem of calculus. That's exactly what you saw in Calculus 1 in the fundamental theorem of calculus. So, using FDC, what do you have? When you differentiate both sides with respect to a, you have that f prime of a is little f of a. Okay, and this is true for all a on the real line. So same, this is all true for all a on the real line. So that's a wonderful result we have. We have that the probability density function is a derivative of the cumulative distribution function for a continuous random variable. So remember that in many situations you'll have one, not the other, and you have to find one from the other. So this is a great equality you can use to find one from the other. And also in many situations you have the probability density function or the cumulative distribution function of a certain random variable, and you're looking at the function of that random variable. So for example, log of capital X or capital X squared. You're looking at a new random variable and you want to find the probability density function or the CDF of that new random variable. What you can do is first find the cumulative distribution function of that new random variable and then differentiate it to find the probability density function. Okay, so this is a very, very important equality that we have in the continuous case, and it's a simple though a very strong result. Okay, all right, so let's now move on to 5.2. All right. So in 5.2, we're going to look at expectations and variances of continuous random variables. Okay. So you remember from the discrete case, what is the expectation of a random variable? In the discrete case, you have that the expectation of a random variable is you sum over all the little x's in the range of x, little x times the probability mass function. Or if you want, you can write it like this, x times the probability x equals little x, any way that you want. Okay? And if you were to guess using this, an analogous definition for the continuous case, what do you think it's going to be? The expectation of a random variable, well, in this case, it's the integral from minus infinity to infinity of x times f of x dx. Okay. And what are different ways you could look at this? Well, there's multiple ways you can look at this. You can do a limit of Riemann sums, and you can say, well, so here's your density, and if you have any x, let's look at a small little neighborhood, go from x to x plus delta x. Let's go from x to x plus dx. And if you look at f of x times dx, well, that is approximately going to be the probability that the random variable x is in that interval. Okay, so the little width times the height. This is approximately going to be equal to this. Actually, I should write approximate. Okay, so you could use this if it's a finite interval where the density is non-zero. You could do a limit of Riemann sums and all kinds of things. But in any case, this is the definition for the expectation for a continuous random variable. Okay, so for the first example, why don't we look at that same lifetime of a car that we saw as our example from 5.1 last time. Okay, so let's take a look. The lifetime of a car, a certain type of car, has probability density function. I'm just going to write PDF for short. And what was that? Remember, we had f of x equals 200 over x cubed if x is bigger than 10 and 0 otherwise. Okay? So let's find the expected lifetime of this car. Okay? Okay, so what is expectation of x? You know, this is the integral from minus infinity to infinity of x times f of x dx. Okay, so in this situation, what will it be? It'll be integral from 10 to infinity because f of x is 0 to the left of 10, x times 200 over x cubed dx. All right. So we'll work this out. You'll have 200 x raised to minus 2 that you need to integrate from 10 to infinity. Okay, it's an improper integral, so I'm writing it as a limit. And what will this be? This is minus 200 over x. And you're going from 10 to b, take a limit as b goes to infinity, and that'll be 0. You plug in 10 and you'll have minus of minus 200 over 10. So what will this be? The lifetime, expected lifetime of this car is 20. Okay, so just showing you this. Okay, so let's take a look at another example. And over here, what we're going to do is look at a function of a random variable. Okay? So, here. So let's suppose the density of a random variable x is given by f of x is 1 if x is between 0 and 1 and 0 otherwise. Okay, so just so that you know, or those of you who have seen this random variable x is said to be uniform 0, 1. It's uniformly distributed in the interval 0 to 1. Okay, and what we want to do is find the expectation of e to the x. Okay, so what do we do now? Here we have the function of a random variable. We know for a continuous random variable, we know how to find the expectation of the random variable. We don't know how to deal with the function of a random variable. So what do? Let's try and find the probability density function of e to the x. How will we find the probability density function? We will find it via the cumulative distribution function and then differentiate it, okay? So let's find the PDF of e to the x by first finding the CDF of e to the x, okay? So let's take a look, okay? So let y be e to the x, all right? So what's the CDF, the cumulative distribution function? What's the probability y is less than or equal to a? All right, that's what the CDF is. Well, before we go into the details of this, what's nice to do for any random variable that you're looking at, it's good to look at the range of the random variable. So let's take a look over here. Y equals e to the x, okay? You know the random variable x is always between 0 and 1. Okay, so what do you think e to the x is going to be? E to the x will be between e to the 0 and e to the 1. So the probability y is between e to the 0 and e to the 1, that's 1. Okay, so that is 1 and e. So y is going to be between 1 and e with probability 1 because x is between 0 and 1 with probability 1. Okay, so the probability y is less than or equal to a. Well, is y ever less than 1? So you know this is 0 if a is less than 1. So if a is any number less than 1, so for example, if you're asking yourself, what's the probability y is less than or equal to 0.75? Well, you know y is always between 1 and e, so that's going to be 0. Okay, and then you ask yourself, what's the probability y is less than or equal to, let's pick a number bigger than e, 3, for example. Then you know y is always less than e, so this is 1. So you have, if it's bigger than e, then it is 1, and if it's a is less than 1, this is 0. Well, between 1 and e, we're going to have to do some more work. So let's write y as e to the x, and let's ask ourselves this question. What's the probability that e to the x is less than or equal to a? Okay, and it doesn't matter since this is a continuous random variable. You could either include one and or the other in either of those. Okay, so let's take a look at this now. Okay, so the probability that e to the x is less than or equal to a. Well, what do we know? Do we know anything about this? We don't know anything about e to the x directly, but we do know how to deal with the random variable x. Okay, so what do? Inside this, let's take a log on both sides. Okay, so this is the probability x is less than or equal to log a. And of course, this is natural log. That's what made the log of e to the x equal to x. Okay, so what's the probability x is less than or equal to log a? Well, now we know. We know the density of the random variable x. That is just given over here on top by f of x equals 1 when x is between 0 and 1 and 0 otherwise. So you know, what will this be? This will be the integral. The density of x is 0 to the left of 0. So 0 to log a of the density of x dx. Okay? And what will this be? What is the density of x, that's 1, so I put in 1 over here, and this is assuming that a is between e and 1, okay? All right, and what will this be? Integrate 1, and this you get, that's log a, okay? So what is this telling us? Well, what was probability e of the x less than or equal to a? That's the probability y less than or equal to a, or the CDF of y, and that is given to us, that we worked it out, and that equals log a. Okay, so let's parse through this. So probability y less than or equal to a. You know that this is the CDF of y. And since there's more than one random variable floating around, it's good to put a subscript. Okay? And this is log a if a is between e and 1. All right? And if a is less than 1, we know it's 0. If a is bigger than e, we know it is 1. Okay? So we have this, and using this, we can differentiate both sides with respect to a, and what do we get? We get that f sub y of a is 1 over a if a is between 1 and e, and we know that f sub y of a is 0 if a is less than, sorry, let's just write it as strictly less than 1. So we have f sub y of a is 0 if a is less than 1. And then we have f sub y of a is 1 if a is bigger than e. So differentiating, you get f sub y of a is 0. Differentiating the constant 1, you get 0 if a is bigger than e. Okay, so now we have the density of the random variable y. Okay, let's put it all together, and we have f sub y of a is 1 over a if a is between 1 and e and 0 otherwise. Okay, so we have the density of the random variable y. You can write x if you want instead of a if you're not so comfortable using the letter a. Okay, so now that we have the density, so let's find the expected value of y. What is the expected value? Is the integral from negative infinity to infinity of y times the density of the random variable y. Okay, so you know that the density is 0 to the left of 1 and to the right of e. So this will be integral from 1 to e of y times the density. What is the density? F sub y of a is 1 over a. So f sub y of y is 1 over y dy. Okay? And canceling, you have integral of 1 from 1 to e, so this is e minus 1, and that's the expected value of y. Okay? So, to find the expected value of y, what did we do? We first found, the cumulative distribution function of y, then we differentiated it, found the density of y, and then we use the formula for the expected value using the density, and we found the expectation of y. This got somewhat tedious. In some situations, you don't have any other go. You will have to find the density of y. But in some other situations, what you can do is you can directly find the expectation of y by thinking of y as a function of x. So you can directly find the expectation of a function of x just like you did in the discrete case. In the discrete case, you remember what you had? You had that the expectation of a function of x was what? You sum over all the x's in the range of the random variable x, g of x times p of x. Okay, so in the continuous case, what do you expect? It is just as you expect. The expected value of a function of a random variable is the integral from minus infinity to infinity of g of x times f of x dx. Okay, and the proof of this, it is in two parts. How do we show this? Well, the proof is in two parts. First part is showing that the expected value of y is, if y is a non-negative random variable, so it is that the range of y is from 0 to infinity. If y is a non-negative random variable, then the expected value of y is the integral from 0 to infinity of the probability that y is bigger than little y dy. Okay, so if you look at this value that you're integrating, it is actually the opposite of the CDF, right? You're looking at where y is bigger than little y. This is the expected value of y. That's part one. And part two, you use this to show that expected value of a random variable, of a function of a random variable, is equal to the integral of g of x times f of x dx. Okay, and okay, and here you're assuming that g of x is a non-negative random variable. Okay, so that is with probability 1, g of x is bigger than 0. All right, so for now, let's just skip these proofs, and you can assume, just as you did in the discrete case, that the expectation of g of x is integral from minus infinity to infinity of g of x times f of x. Okay, and using this, you have certain basic results. So what is the expectation of a times x plus b? Well, what will this be? This will be the integral from negative infinity to infinity of a times x plus b times the density of the random variable f of x. And by linearity of the integral, you have integral a times integral negative infinity to infinity x times f of x dx plus b times the integral negative infinity to infinity f of x dx. Okay, now stare at this a moment and see, what is this? The integral from minus infinity to infinity x times f of x dx. What do you know? What is this? This is the expected value of x. And what is this? Integral from minus infinity to infinity of the density. You know that this is supposed to be 1. So this is just a e of x plus b. So when you have a linear function, then it is just the expected value of a linear function is just the linear function evaluated at the expected value. But this is not normally the case. So please do not make this mistake. Expectation of g of x is not equal to g of the expectation of x in general. Okay? This is only true when you have g is a linear function. And if it's not a linear function, you do not have this being true. Okay, and you can see using this, well, what is the variance of a random variable x? Okay, you know the variance of a random variable x, by definition, is the expected value of x times the mean whole squared. All right, and we've gone through this. What this turns out to be is the expected value of x squared minus mu squared, or that's the expected value of x squared minus the expected value of x whole squared. All right? And how would you find the expected value of x squared? What is this? Well, just from the above, you know what this will be. That's your g of x. Okay? So this will be the integral from minus infinity to infinity of the function times the density. All right, so that's your expected value of x squared. And you use this to find the variance of a random variable. Okay, so as an example, let's just go back to the car situation. And you had that the density was what? 200 over x squared if x is bigger than 10 and 0 otherwise. Okay, so what is the expected value of, we want to find the variance of x. We already saw that the expected value of x was 20. We already saw that. What's the variance of x? That's the expected value of x squared minus the expected value of x whole squared. So let's try and find that. What's the expected value of x squared? Well, let's take a look. This is going to be the integral from 10 to infinity of, sorry, this was a cube. Let me fix that. X squared times 200 over x cubed dx. Okay, so that's integral from 10 to infinity of 200 over x dx. So that's 200 log x going from 10 to infinity. Okay, and what do you have? This will be infinite. All right, so in this situation, what do you have? That the variance of this random variable x is infinite, because expectation of x squared turned out to be infinite. And that's not unheard of. That's okay that in certain examples you do have that there's so much variation, there's so much spread of data that the variance is infinite. Okay? And if you want to take, let's take a look at another example. Let's take a look at the situation where you have that f of x is 1 when x is between 0 and 1 and 0 otherwise. Okay, so random variable x has this probability density function. Let's find the variance of x. Okay, so what will this be? Expectation of x squared minus expectation of x whole squared. All right, so I'm just going to write it down as a whole string over here, evaluating all of these quantities at once. Okay, so what's the expected value of x squared? It'll be integral from 0 to 1, x squared times the density, which is 1, dx, minus integral 0 to 1, x times the density dx, and then we're going to square this whole thing. Okay, so this is x cubed over 3 going from 0 to 1 minus, what is this? This will be x squared over 2 going from 0 to 1, and then we're going to square it. So this is 1/3. And what is this? You plug in 1 and you get 1/2, and you square it, so you get 1/4. So this answer is 1/12. And anyway, along the way, you also saw that expectation of x is 1/2. Okay, and recall that I said that's the uniform 0, 1, and 1/2 is in fact the middle of the interval 0, 1. And we will see in the next section, we'll look at uniform random variables. Okay, so that's the end of 5.2. And in 5.3, what we're going to look at is a uniform random variable. Okay, I hope this made sense. Please don't forget, email your questions.